This example is from MGF 1107, section 14.3, when we're asked to use the nearest neighbor algorithm to find a Hamilton circuit. As you can see from this problem and the chart, the chart has the cost of one-way flights between several U.S. cities. As shown below, there's 5 different cities: St. Louis, Kansas City, OKC, Des Moines, and Little Rock. And we're asked to determine the minimum cost for a trip that starts in Des Moines, down here in Des Moines, DM, and it travels to all other cities once, then returns to Des Moines. Now the key thing here is it's circuit. Since we're starting in Des Moines and we want to visit all the other cities and then return to Des Moines. So it's a circuit because we're starting and ending in Des Moines. And it's a Hamilton circuit because we want to visit each vertex exactly one time and not use all the edges that are in the graph. So in order to do this, we're going to use the nearest neighbor algorithm. Now the nearest neighbor algorithm only finds an approximate solution to a traveling salesman problem. It does not find the minimum or optimal solution such as the brute force method does. Yet it is much faster than the brute force method. So again, the nearest neighbor algorithm finds an approximate solution, and sometimes we do get lucky and it is the optimal or the lowest solution, but not all the time. And what the nearest neighbor algorithm says is start at your beginning vertex, in this case city, Des Moines, and from Des Moines you can travel to any of the other cities. Well, we want to choose the cheapest, the least expensive, the one that costs the least from Des Moines. So if you look at the Des Moines row here, we won't construct the whole complete graph. We'll just use the chart to help us. So from Des Moines, the cheapest city to go to would be KC, Kansas City. So we're going to form that edge there. We're going to fly to Kansas City for $195. Since that's cheaper than $445 or $401 or $352. And then from Kansas City, which is this row, we do not want to go back to Des Moines yet. So what we do is we pick the cheapest flight to another city. So in this case, if you look at that row, the cheapest or the least expensive city to fly to would be St. Louis. So we go to St. Louis. That's 48. Now once we're in St. Louis, that's the top row, we want to go to a city that we have not already been in. So again, we can't go back to KC or Des Moines. So we have to go to one of the other cities. So look at that row for St. Louis. It's 48 to Kansas City, but we can't go back there. Oklahoma City is 70. Des Moines, we don't want to go back there yet. And Little Rock is 64. So we're going to go to Little Rock from St. Louis at a cost of $64. And then again, you're not left with much at the end. Some people call it a greedy algorithm because you're greedy and you take the lowest price. But that at the end you're kind of stuck with the last two edges of the graph, because once you're in Little Rock, you must go to Oklahoma City, which you notice it's not the lowest. So you have to go to Oklahoma City. Because remember, this is a Hamilton circuit, so we want to visit each vertex or city. We don't want to use every single edge between all of them. We want to just visit each vertex at the lowest cost. And then we're stuck. Once we're in Oklahoma City, we're stuck that we have to go back to Des Moines, and that's where it hits our wallet, 401. So again, this one might not be the optimal solution as the brute force method would give us, but it gives us a ballpark approximate solution. So if we add all those values up, we will get an approximate estimate of the minimum cost. So again, that would be, we started off with 195, then we went to 48, 64, 96, and our greediness hit us at the end because we were stuck with taking the flight that cost $401 back. So if you add that up, you get what, 13, 17, 23, 24? Carry the 2. 11, 15, 21, 30. It cost us $804 for that circuit. And again, that's a Hamilton circuit because we visited each vertex exactly one time. And it might not be the optimal solution, but it is a quick way to get an approximate solution.